Hello, welcome to your first video involving the periodic table. And so it's been a long time coming. We are now officially talking about the periodic table. We are soon going into chemical reactions and how different elements interact with one another. All of the information we've learned up until now all leads into this, but you needed to have the basic understandings of atoms, protons, and neutrons, electrons, and all of those interactions, how they behave, and different types of energy levels. And so again, we have done all of that, and now we are leading into the periodic table, which when you think of chemistry, you definitely think of elements, reactions, and making things explode. So that is what we're getting into. And I am going to try to keep these videos short. According to Griffin O'Neill, they are way too long. I will work on that. All right, so the things that you should be able to do after this video is you should be able to describe some of the early attempts to organize the chemical elements, understand how Mendeleev organized his periodic table, know the improvements that Moseley made to Mendeleev's table, know the periodic law, and finally describe various components of the modern periodic table, including periods, groups, metals, nonmetals, and metalloids. We are going to talk about all of this. We will go through in class and label our periodic tables yet again. Right now, your periodic tables are labeled with SP, D, and F. We are going to go into even further detail and look at elements on a bigger scale now. So not just subatomic particles, but now looking at them as their physical properties, things that we can actually see, how they interact with one another based off those physical and chemical properties. All right, so the first thing we need to talk about is the periodic table and how and why it's organized the way it is. There have, in history, been many attempts to organize this table in a very logical way. And the reason for this is because when elements were being discovered, it was noticed by the science community that there needed to be some organizational method to observing these elements, to observing their chemical properties. Because at this point, before the periodic table was created, there was patterns that were seen but not really described in full detail and not really supported because there was no organization to the process. So we're going to start at about the year 1700. At this point, only a handful of elements have been identified and isolated. Several of these include copper and lead. These have been used for long periods of time. There are some elements that are thousands of years old as far as discovery goes, and then there are some that are still being created today. The periodic table we have in class is the most updated form, and you'll notice that some of the elements are not in bold letters, and I'll explain why when you come to class. But with the ever-increasing number of elements in that time frame, chemists recognize that there may be some kind of systematic way to organize the elements. So I am going to talk about a couple of guys first before we get into the big players in the periodic table organization and describe some of the ways that were done but not necessarily accepted. So a logical way to begin to group elements together was by their chemical properties. Scientists recognize that some elements act like others, or they're very similar to one another, and so they thought, well, they probably should be organized in that way. So what was done was they were put into separate groups based on how they reacted with other elements. So in 1829, there was a guy by the name of Johann Derbenreiner, and he placed groups in these things called triads. So what he did was he took three elements, like lithium, sodium, and potassium, and based on their physical and chemical properties, grouped them together. He found that the atomic masses of certain elements, and in my example, lithium, sodium, and potassium, those atomic masses averaged together to look like the other. So for example, the atomic mass of lithium and potassium averaged the atomic mass of sodium. These were three elements, and they also displayed similar chemical reactivity. They vigorously reacted with other triads. And so this is great, right? All of this method works. And unfortunately, the periodic table is not classified that way because of the fact that the triad system does not work for every single element, or does not explain some of the reactions of particular elements. So then here comes a new guy by the name of John Newlands. And he arranges the elements in increasing order of atomic mass. And he noticed a trend. He noticed that every eighth element exhibited similar properties. He called this relationship the law of octaves. It is quite unfortunate, though, that at the time that he was creating his periodic table, there were elements that had not been discovered yet. And so his trends did not explain for abnormal elements. So, for example, calcium, which is a very heavy element, that trend or the law of octaves doesn't explain that. So unfortunately, Newlands was ignored and he was kind of made fun of for this idea. And it wasn't until years later that, I guess not years, but a few years later, that Newlands finally gets some credit. So again, remember, he organizes them by increasing atomic mass, and he notices a certain trend. This leads us into Mendeleev, and he is known as the father of the modern periodic table. And the really one of the main reasons why he's noted as the father of that is because he published his paper before other people. So great if you're timely. But he had a lot of observations and cues, and this led him and led other scientists to really revamp his periodic table. So in 1869, a Russian chemist and teacher, shout out to teachers, published a periodic table of the elements. And so what he did was he organized information on like 3x5 cards. So he got information on different elements and he put them on different note cards. And so this way he could easily arrange the periodic table how he saw fit. And he discovered that when he placed them in order of increasing atomic mass, certain similarities in chemical behavior repeated at regular intervals. So poor guy Newlands was made fun of, and now you have Dmitri Mendeleev who's coming in and doing the same thing, and he's now noticing more patterns. The advantage that Mendeleev had was that he had more elements at his disposal. More elements were discovered at this time frame, and so that's why he had more to observe. This type of repeating pattern can be referred to as periodic. So whenever he saw these repeating intervals, we're going to note it as periodic or some kind of trend. Other examples of periodic behavior include the movement of a pendulum. So that's just another example. Or you can think of the orbit around the Earth as a periodic behavior. Just giving you examples of the term periodic. So anyways, Mendeleev comes up with his own beautiful table, and I am going to show you a picture of this in class, and we're going to make some observations on it. But when we're looking at his table, if you look from the top to the bottom of his columns, the atomic masses increase. And so what he noticed is that elements in the same horizontal row are groups of elements that were known to exhibit similar properties. And so Mendeleev's periodic table is a bit different than what ours looks like now, but it was a great way to show different insights. So another insight that Mendeleev illustrated was by the elements tellurium and iodine. And if you look, and I'll show you this in class again, tellurium is listed before iodine, even though its atomic mass is higher. And so Mendeleev, what he ended up doing was reversing the order, because he knew the properties of iodine and how those are similar to fluorine and chlorine, bromine, and all of those other elements. So he made some assumptions. And even though these were an error, he still had such a huge understanding of these elements that he could essentially predict certain elements and their presence, but the fact that they weren't discovered yet. So, and again, I'm going to show you his table in class, and we are watching a video, so we will talk about Mendeleev in great detail, and it'll show you his original periodic table. And like I said, he had such a huge understanding that he predicted that there were some elements that existed but were not discovered in his time frame. So he believed that elements with atomic masses of 68 and 70 would eventually be discovered, and that their chemical properties would fit the trends of his periodic table. So he left spaces for these elements that were not discovered. And if that's not a great understanding of periodic trends, then I don't really know what is. And so he ended up predicting the atomic mass of an element he called Eka aluminum. And he said that this is going to go before aluminum And it's known as, now it has been discovered, and it's now known as gallium. So he gave it a name. He said the melting point was going to be low. It was going to have some kind of density, and it was going to have a similar formula close to aluminum, but he didn't know what. This ends up being later discovered, and now it's known as gallium. So pretty impressive stuff. So Mendeleev, this periodic table gained super wide acceptance within the science community, and it earned him the credit as the discoverer of the periodic law. And we are going to talk about the periodic law here in a little bit. But again, what he's doing is he's noticing trends within the periodic table, noticing patterns. So that's what I'm talking about when I say periodic. We're noticing these patterns or these trends that occur and will always occur. There are a few exceptions to this rule, but for the most part, Mendeleev had a really, really grand idea. The periodic law. So, like I said, Mendeleev's table was organized by increasing atomic mass. Years later, a guy by the name of Henry Moseley, and you should recognize him as a physicist that contributed to the atomic theory, he ended up noticing that just based off of the idea of now knowing about electrons and protons and neutrons, that the elements should probably be arranged in order of increasing atomic number. So when he did this, the issues that came along with Mendeleev's periodic table completely went away. So I talked about beryllium and iodine earlier, and so when we switched those back based off their periodic tables, those trends worked perfectly. And so this came up with the idea of the periodic law. Periodic law is when elements are arranged in order of increasing atomic number. There is a periodic repetition of their chemical and physical properties. So as we look at the periodic table, they are arranged in a way that's increasing periodic number, and they have similar chemical and physical properties. And we're going to talk about the groups and periods in class. And you'll notice that some elements even look similar to each other and the fact that they're all arranged in the same row is not a coincidence. The modern and periodic table. So we've talked about Mendeleev and Moseley, and they're both kind of given dual credit, but Mendeleev again published his ideas first. So he is the father of the modern the father of the periodic table. Henry Moseley comes in and revamps it, and this is what we know as the modern periodic table. So since these two have put out their periodic tables, there are new elements that have been discovered, and there are also some that have been man-made. So each one of these fits properly into a group of elements with similar properties. The periodic table is a way of arranging the elements in order of their atomic numbers so that elements with similar properties appear in the same vertical column or group. So we need to distinguish what's a group and what's a period, because you've probably heard me say these words in class, but I have not officially taught you what a period and a group are identified as. A period is a horizontal row of periodic table. A horizontal row on the periodic table. So if you don't know what horizontal is, you can always think of going that way. So H, it moves all the way from like right to left. And then a group is a vertical column. So vertical, you can think of like an arrow going up and down. Those are ways that I remember it, and it never goes wrong. But if you look, especially when you go down groups, there are a lot of patterns that follow with these particular elements. But let's focus on periods first. So again, the period is a horizontal row. There are 7 total periods in the periodic table, each beginning at the far left. A new period begins when a new principal energy level starts filling with electrons. So remember, we talked about n equals 1, n equals 2, n equals 3, and each one of those fills a different sub-level, so S, P, D, and F, before we get to the next one. Again, we'll talk about this in class, so don't worry if you don't remember from a couple weeks ago. Period 1 has only 2 elements, hydrogen and helium, while period 2 and 3 each have 8 elements. Periods 4 and 5 each have 18. Periods 6 and 7 each have 32. Remember that big group, the lanthanides and actinides series, is moved on out, even though it is technically a part of the periodic table. A group is a vertical column of the periodic table. There are a total of 18 groups, and there are 2 different numbering systems associated with them. So that really sucks because you're expected to know both of them. The United States happily uses the 2-letter system. And so what this means is that there are 8 total groups in the group A, and then the middle groups, known as the transition elements, are labeled with Bs. Unfortunately, that's a little bit confusing, and so the rest of the world uses the system of 1 through 18 from left to right, and I will show you both of these in class. But in our class, we have both systems labeled. Actually, I lied. The B system is not labeled, but on my old periodic table, it is. So United States, once again, has proven that we like to be different. But don't worry, we're going to learn about them both. Yay! I will be adding notes in regards to man-made items, or excuse me, not items, elements in class. So make sure you leave some room at the end of this slide so that we can add those. All right. Now, when it comes to looking at elements, they have different characteristics. We have what's known as metals, nonmetals, and metalloids. Elements can be classified in one of these 3 ways. So there are 3 different ways to classify an element. The biggest way is metals, nonmetals, and metalloids. And then classifying by period and/or group is useful because it's based on electron configuration. We've already talked about this, but don't worry, we will review again. A metal is an element that is a good conductor of heat and electricity. So they're really malleable, they're ductile, and I can tell you what these mean in class if you don't remember from when we talked about physical properties. They're shiny and they reflect light well, so they have really nice luster. They are typically solid at room temperature. I shouldn't say typically, I mean they all are solids at room temperature except for mercury, which is not. Has a very, very low melting point. 80% of elements are known as metals. And that leaves the other 20% that make up nonmetals and metalloids. So your nonmetals are the complete opposite of metals, which makes sense, right? They are not very great, they're very poor conductors, they're poor conductors of heat and electricity. So if you're going and you try to burn some plastic, you're not going to do too hot when you're trying to conduct heat. Sorry, it really sucks. And so many of these properties of nonmetals are complete opposites of a metal, like I said, but they don't have specific types of properties. So metals, we know they're solids at room temperature. Well, that's not the same for nonmetals. Nonmetals can be solids, liquids, or gases at room temperature. A majority of them are gases, but not all of them. And another thing, they are not all of them, because not all of them are in a solid state, you don't really know like some of those physical characteristics. So some of them may be brittle, but not all of them. The solids that are solids at room temperature, they don't have a luster. Their melting points are generally pretty low. And I mean, most of these nonmetals are also found on I can't think right now, but I'm pretty sure that's the right side of the periodic table. And that includes like carbon, nitrogen, oxygen, fluorine, all of the noble gases. But again, we'll talk about that. A metalloid is in between a metal and a nonmetal. That means it has some properties of a metal, some properties of a nonmetal. Silicon is a really good example of a metalloid. It has luster like a metal, but is brittle like a nonmetal. Silicon is extensively used in computer chips and other electronics because its electrical conductivity is in between that of a metal and a nonmetal. You also can hear them called semimetals, and they form on the periodic table what's known as a stair step. Again, we will label this on your periodic table. And that's all I got for you. I'm fairly certain this video is too long according to Griffin O'Neill's standards. I apologize. I really tried, and I tried to talk really fast, but that didn't help, I guess. If you have any questions, please ask me on Edpuzzle.